Hello everyone, welcome back. So today we'll start a new topic and that is on compliant mechanisms. We often call it flexures or sometimes also referred as elastic mechanisms, and we'll learn about it briefly. And what we need to understand that these are the elements which are very important if we are designing products or machines or any element or any instrument for precision. So, first we'll try to see some examples here, and this is out of what we did in our lectures courses here at IIT Delhi. So, this is designed by students in our lab at IIT Delhi, and what you notice that most of these designs or mechanisms, they are compliant in certain directions, and that's why we call it compliant mechanisms. So it has a directional compliances and stiffnesses as well. So what you realize that most of them are 3D printed. So and it's very good for illustration. So you can see these designs. So this is the CAD model also, and yeah, most of them are 3D printed, and this one is, what you can see is, we use wire ADM to machine it out, and we can identify the elements here. So what we have observed here that they are monolithic design. So in most of the cases, yes, in some cases one can say that it's assembled. So we printed parts and then assembled it. So likewise, we can also fabricate or machine the functional parts, and then we can assemble it. But many times they are built out of one big chunk, and that's why we call monolithic design. So out of one block, we machine it out or we build it slowly. So we have a 3D printing technology available these days. So that can be also done, and not only with the plastics or polymers, but we can also use metal 3D printers, and we can make these mechanisms out of that. So that's why it's called monolithic design. We also observe that yes, the range of motion, what we are talking about is they are still within elastic region, and yes, so they can always come back to their original positions, and that's why we are calling it elastic mechanisms as well. So they can bend, they can twist, and they can elongate depending on the design, and yeah, in certain directions we can move it very freely, so we have the compliances in those directions. But in some directions the stiffness is very high, and that can be considered as a constraint direction. So and that's why the next one, what we are calling, is controlling degrees of freedom, or call it degrees of freedom and constraints. What we also realize that there is a relative motion, but there is no sliding friction. They are not rubbing against each other, but all the motions what we are getting is because of the elastic deformations, and there is no contact, physical contact between the parts, and therefore there is no friction involved, and because of that, since it's an elastic mechanism, it can always come back. So therefore we can ensure higher precision, and that's why it's a very important to understand how compliant mechanism works and what is the role if we want to design precision systems for any application. So since they are monolithic, they are elastic, they have certain degrees of freedom compliances. There is no friction involved. Precision can be achieved, and therefore miniaturization is also possible. The scaling. So what we just saw, that they are all uh, in the macro range. We can feel it, we can see it, and it's good for illustration in the class or in the lectures. We can build those setups and can demonstrate, but nothing stops us from making it smaller. And since there are no physical joints there, so there is no need of bearings, bushings, or even for clamping there are no nuts and bolts. So it means the number of parts reduce considerably. At the same time, there is no need to assemble those smaller components. So it means we can go to even wafer level or nanometer level kind of dimension. So if we want to make any kind of actuators, or so for instance call it MEMS devices, so actuators, call it micropumps. So all those things, so all these mechanical design, the mechanisms can be embedded in a very small footprint and maybe of the size of a chip, and therefore it's possible to develop these kind of devices and actuators these days. So all these kind of designs you see, they are in, they can be fabricated out of silicon, and they can be packaged, and yeah, the MEMS devices, MEMS actuators for biomedical application, for automotive application, for any dynamic application. So actuator sensors, if you want to develop, that can be easily achieved. So once we understand the elements, once we know that these are the functional parts and how it can be how it can work, so these designs can be embedded and can be manufactured at a wafer scale, and we can design these elements precisely to any chip. So miniaturization is very much possible in this case. So what we do, we try to understand through some examples what we have done throughout these years. And one should also understand that these applications, the compliant mechanisms, is not limited to MEMS or NEMS or to these micro actuators kind of application or very precise application, but it can be embedded to normal design, so day-to-day design also. And very often we see these things embedded in the designs, so we should be able to appreciate that as well. So for instance, in this case, so one of the initial work, and some student worked on it, so we have designed a flexure based passive gripper for robotic application, for pick and place application. And here you can see a pallet, and that has to be picked and dropped. So of course there can be uh, many actuators, or we can have sensors and actuators, and we can use the control to grip it. But what we understand and how we work generally, that intuitiveness can be built in the system using these compliances. So for instance, if you want to pick up some part and precisely put in a certain kind of tube, we can use that compliance. So for instance, in this case, well, the constraint is only in the pushing direction, we want to place it, but we want that because of the interaction between the hole and the object, this should comply and it should find a way on its own, and therefore we design based on that principle. And you can see there are a lot of compliant parts here, and we can go in the detail. The functional part is this folded sheet flexures, and the what we understand that this is the constraint direction, the fold line, and we use that concept, and we have these configurations in series, and then we are able to get that. So we can place it, it can move around, and even for picking we use this kind of cantilever structures, and it can push and can get uh, we can grip it, and when we want to release we can push it with another part and it can be released. So we have already implemented that design, and use the first we use the 3D printed part, and later we got the metallic part fabricated. We use wire idiom and then uh, show the results. So we also file patents and publish it later. So very good use of compliant mechanism, and this is just to show that even 3D printed parts can show those functionality, and we can be sure that whether it's going to work. Another example is for developing or fabricating microfluidics chips, and there we use the precision hot embossing machine. So we developed that. So again, very frugal design, but we use the concept of precision machine design, and use the compliant mechanism. So what you see here is a straight guidance, and what is desired is when we put the substrate and when we apply the force, and we are providing the heat, so that the feature, whatever the feature at the bottom what we have, it get transferred to the substrate precisely without any damage. What is required is only the jet motion that should be there, and both ways when going down and coming up. It should not, if there is any kind of misalignment or kind of this kind of thing, the other movement in theta direction, it will destroy the edges and then will not get a very good quality microfluidic chips. So understanding that requirement we have built up. At the same time, what we also understand that heat is involved, there is a heat source, so there is going to be expansion and contraction, and it should be designed in such a way that there should be a thermal center, and at the same time it allows expansion if there is a heating, and then when it's cooling down it should shrink back or contract without building any kind of stresses due to over constraints. So we also use that principle here, and used it, and you can see that the template, master template, the features what we have can be transferred to the PMMA substrate. And again we got the patent, and later we got the publication as well. So again, this is a very precision setup, and we wanted to develop a microfluidic chip for our own usage, for our own use. Many times we have to send the specimens abroad and get the chips for doing the experimentation. But what we realized that knowing these things can lead us to develop our own setup, our own instruments, and definitely it can be scaled up and can be transferred for mass scale production of microfluidic chips. Another interesting example, and many times that's what we use compliance for, and this is for robotic application. So robot assisted minimally invasive surgery. So if you are aware of Da Vinci robots, and it's the state of the art, and there are many such commercial or research minimally invasive robotic surgical systems are there, and most of them are based on double parallelogram concept. And what is good thing about it is there is a RCM, remote center of motion, and which can be aligned to the insertion point of the patient. So when we insert the instruments here, so the whole is fixed by the design. It's not supported on the patient, but is supported by the mechanism itself. So no matter how you move in this direction or this direction, that point is fixed to the hole, and that's why it's uh, very good, because we don't have to control actively the insertion point. So once we set up, it's there. But the basic premise and basic assumption is these two parallelograms, 1 and 2. So these have to be parallel. The link length, everything has to be there. But when it comes to production and manufacturing these kind of things, what we realize that yes, we are limited by tolerances. So the link length may not be same. There might be some differences. So what happens? So yes, we try to study the sensitivity if the link lengths are different, and then what is the way and how we can adjust, realign things post assembly. It means we may need some mechanism to adjust in the range of maybe zero point 0.1 or zero point 0.2 millimeter and get rid of that tolerances. So that's the importance of compliant mechanisms. And when we study about controlling degrees of freedom and constraints, what we also understand that okay, the adjustment and alignment requirements are very important if you want to achieve precision. So if you want to achieve this RCM, this has to be parallel, and for that it's important to have those link lengths in place. So the 1 and 2, those parallelograms should be parallelograms. It should not be trapezoid. So again, this is the concept, and in order to adjust that, what we try to do is, you see here, this is the compliant part, compliant mechanisms we introduced. So we made one of the joints floating, and in such a way that you can see there is a micro screw here and here, so it can adjust. So after assembly, we can check and we can readjust, and what it does is, whatever is the center here, it can be moved in this direction and this direction. And what are the elements here is, you can see here, so which we call it sheet flexures. So thin leaf spring or sheet flexures we call it, and we'll study about that. So this is the enabling technology, and we embedded that in our design. So these are the examples, few examples, and yes, it's we have done in our lab at IIT Delhi, and at various stages, and we have developed these products. And if you get the chance, you can always visit my lab and see these things working. So we have some more examples, and as we progress, we will talk about those cases one by one. So in general, if you encounter these kind of features which is generally not known, so they they don't look like normal parts, so like yeah, any kind of torsion, the shaft, or the any kind of connectors, gears, springs, they may not look like that, but they look little strange, different kind of geometry. Uh, Usually we are not aware of if we are doing engineering, and unless you are exposed to this kind of literature, you find it difficult. So I think you may be able to appreciate those designs when you encounter those things in the real machines, when we get from abroad or from elsewhere, and when we need to service them and do the maintenance, and something not working, and when we open the machine, I think we should be able to understand why those features are there, what are the functions, and we should be able to operate on those machines confidently. At the same time, if we are referring to any kind of literature, so all these kind of features, if we see, or in mechanisms, if we see these kind of features, or even this is like a spherical joint, doesn't look like a spherical joint, but this is this mimics the spherical joint, and many features, such features embedded in different places. So I think after this course, one should be confident enough to understand and work on it. So we just try to summarize why flexure mechanisms, what are the advantages. So of course, miniaturization is the key. Nothing stops us from making smaller and smaller parts, or robots. It can be small insects like robots. It can be for microfluidic applications. It can even go to our blood streams and can deliver drugs. So whether these features can be of the order of micron or even below micron, it depends on what kind of manufacturing capability if we have. So suppose even the metal 3D printer, if we can achieve something of the level of the order of like nanometer, of course we can make those smaller devices. Friction is not involved, so therefore the precision, the the forces of that order, if there is a friction involved, that can be catastrophic, so that is not involved. Yes, we can control degrees of freedom, so we can adjust, we can realign, and can get the precision what is required. So of course this is what is desired, and what are the advantages if we are using any kind of flexure or compliant mechanisms, and that is the reason we are able to achieve different kind of MEMS or NEMS actuators or sensors. So if we look at the limitations, of course it's elastic mechanism and it's a monolithic design, so the range of motion is always limited. But most of the cases, what we realize that we don't need a very large range of motion. The range of motion might be of the order of maybe in microns or arc seconds, or within a millimeter. So depending on the requirement, we can always have these designs in place. What is also important to understand that we can always build these mechanisms on top of regular mechanisms or mechanisms with the coarse movement. So any conventional design, ball screw or the linear guides what we have. uh, so they are no more, although in today's time we can call it precision, but when we are talking about 1 micron kind of precision, they may not be precise enough. So these things can be built up on top of that, so we can have a coarse motion with this conventional design, and the end part we can have these compliant mechanisms or flexures to do the final adjustment or alignment. So the limitation is a limited, the range of motion is limited. Of course, it's mainly because of the stresses developed. So you can see that whatever we are doing when we design compliant mechanisms or these flexures, we are using the geometry, and whatever is taught at undergraduate level, we just do the opposite, and we have a very small slenderness ratio, so or what we can call it higher slenderness ratio, and abrupt changes in the geometry. So there can be large stress concentrations. So we have to be aware of. Sometimes it can be also for dynamic application. So we have to be aware of fatigue loading or fatigue stresses. What is generally mentioned that for most of the cases, if we find the stress level, the maximum stress level, and if we are limited to the range of motion, which is just half of that, then most probably we don't have to worry. So, but of course, there will be stress buildup, and we have to be aware of that, and that's why the range of motion is also limited. At the same time, the stiffness is in the bearing direction, in the constraint direction. We have to be also aware of that. And if there is a load in that direction, then we may have to check the stiffnesses if it's going away from the neutral position. What is also important that it's a elastic mechanisms, so it has a certain stiffnesses. It has certain stiffness. It means wherever we want to put it, or if there is any deviation from the neutral position, the stiffness always acts against the actuator, and it has to overcome the potential energy stored, and therefore the actuator has to be powered all the time. If not, then we may have to find a way. Or another way is we have to design for zero stiffness or lower stiffness. So there are different methods also to design for a stiffness. So what we studied in the earlier lectures is designed for stiffness. So the main concern was, or main emphasis was, to design for higher stiffnesses, and that's what we talk about. But when we talk about compliant mechanisms, it's the other way around. We want to have more compliance. So in the desired degree of freedom, we wanted to have less and less stiffness and maximum compliance. It means we may go towards zero stiffness, and there are ways to design such mechanisms, and or there are methods to design for zero stiffness. So we will be talking about those things as well. So the key equation, or what we understand, that if we are designing anything for compliance, it has to be either bending or torsion. And in most of the design, what we observe that we are using the bending of the member, and we can achieve the desired compliance. So we'll talk about that, and we just go through once a recap what we studied in our solid mechanics or even mechanics courses. So if you have a cantilever, and length L, and if the force, we apply the force F, and the deflection, associated deflection is in the direction F is Y. Similarly, we can also apply moment M, and there is associated angular deflection phi. So what happens? So we just go back to the basic derivation, and at any point x, if we take the cross section and we try to calculate, what we find that the bending moment is m, this is m, and due to F we have L minus x. So F into this distance that is L minus x, and they are in the same direction, so we add them. But we also understand that this is how the bending moment, so bending moment at any section at, at point x is related to the second derivative of the deflection d2y by dx square, and that's where we also first time relate to EI, the Young's modulus, and the area moment of the beam. So we need to know the cross section, so EI values, so which is called flexural rigidity. So we are not going for a very large deflection. We are limited to small deflections only, and that's why we are only restricted to linear and Euler-Bernoulli equation. So if the deformation are large, yes, we can always refer to the advanced solid mechanics books, and we can do the correction. But the idea of this course is to use these elements for design, for machine development, for machine design. So we want to do some rough calculation, back of the envelope calculation, so that we know what is the range of motion, what are the stiffnesses we are talking about, and therefore we can talk about this basic bending equation. And so this is the key. I think we should always remember d2y by dx square is equal to m by EI. And if force and moment both acting, then we try to find. So bending moment, function of x, we place it, and this is the basic equation to work with. So if we want to find the angular deflection or dy by dx, we integrate once. So 1 by EI, and then FL with respect to x. If you integrate, we get FLx. Then we have minus fx, so we get fx squared by 2. We have m, so m will give mx, and then a constant c1. So I think I'm just trying to go one by one so that we can understand, and if we forget, we can always go back and check it. So if we integrate once more, we can get the deflection, and likewise we can get from FLx, we get FLx squared by 2 minus fx cubed by 6 plus mx squared by 2 plus c1x plus c2. So that is, these are the function of y, so at different point, but we have to find the constants. So these are the, once we integrate, this is what we get, d2y by dx squared, dy by dx, and y. And the boundary condition at point x equal to 0, the deflection, the angular deflection or the slope dy by dx is 0. So therefore, what we get is c1 is equal to 0. Similarly, if we see the deflection here, that also leads to c2 equal to 0. So it means both are 0. So if we write in terms of x, so the angular deflection and the y displacement with respect to x, this is the formulation we get. What we are interested is what will happen at the tip at x equal to L. So if we substitute, we get y. So the total deflection, so it's because of both, because of force F is FLQ by 3EI, and because of m, bending moment, pure bending moment there, ml squared by 2EI. Likewise, we'll also get the angular deflection at the tip, at the end, which is FL square by 2EI plus ML by EI. So we can rewrite here, and of course this is at the tip. So when x equal to L, and we can always rewrite it in terms of this y and phi. So in matrix form we can convert. So at this end we can write y and phi, and at this end we can have F and M, associated forces. And what we realize here is it's very easy to work with. So y, so F is there. So with respect to F, what the coefficient of F will come there. So LQ by 3EI. With respect to M, this is what we have. L square, the coefficient of M, L square by 2EI. Likewise, from this equation phi, we can get these two terms. So in generally what we can write, this y denotes both y and phi, and it can be written as some matrix form, and then this is F. F is both includes this, and y will include this, and this is 2 by 2 matrix, 2 by 2 matrix. So if we just relate, and if we simply write y equal to some matrix, so call it C, or call it C. But it can be also written as, so here y by f is nothing but the compliance, So it's a compliance matrix. But it can be also written in terms of f equal to x, or I call it y or call it x. X means displacement. So I think yes, general rotation is for displacement we write x, but x is not the same x, but this is the deflection matrix. What is here? So here we can call it K. So this is the stiffness matrix in that case. So for a simple cantilever beam, we can write F equal to Kx. K is the stiffness matrix. So this may be a homework exercise for you. Can we derive it from these two equations? Because yes, it's two simultaneous equation, and we can always rewrite. Of course, we can get the inverse and can find it, but we can work with these two equations and rearrange, and we can also write in terms of f equal to kx. So maybe what we try to find is f some function of f1 y phi and m equal to some function y phi, and then we should be able to write in terms of matrices f equal to kx. So we'll try, and this is something we'll be using most of the time. So for general case, if f and m is working at the end, what is the overall equation, and what is the relationship between the forces and the deflections for general case, and then for individual cases we can apply boundary conditions and can work with that. So I think a very good exercise, and this is kind of mechanics one has to know if you want to work with precision. We don't have to work with the very sophisticated mass or dynamic equations, but I think if we need to work with the design and want to develop uh, this kind of setup and use compliance for that, I think these kind of simple derivations are good enough. So we'll continue with this and take up some more examples, some cases, and we'll talk about different kind of flexures compliant mechanisms one by one in the coming lectures. Thank you.